Welcome back to another Webinar Clips video, our series where we present selected clips from our TMG Plastics EDU webinars. Today we will be showing a sneak peek of a webinar presented by Paul Grauman. His webinar offered an overview of the most important considerations when converting a metal part to plastic. The Madison Group has several upcoming webinars that you can register for on our website, which will be linked in the description below this video. On this page, you can download the full presentations for our latest TMG EDU webinars. Without further ado, let's get into this webinar clip.
Coupling nuts used in plumbing. This is a very common failure that's been around for many, many years. The reason I'm showing you this is that for many, many years, the conversion from metal to plastic was almost 100%, meaning that the design of the plastic was almost a straight knockoff from the metal. You can see that's almost the case here. Yes, there are some little bit of ribbing, but besides that, everything else is almost identical. The threads inside are identical, the type of thread and how long the thread goes down. We'll see that in a second, okay? Again, you need to start from the beginning. Put the metal part aside. Certainly you can get some information from that, but you need to start with the design rules for plastic. Now, these things fail from creep rupture. Creep rupture is a stress below the yield point of the plastic, and it occurs over time from a constant tensile stress, okay? Basically, the molecules are disentangling over time from this constant stress. And you'll see this in a second, that cracks are occurring in a brittle mode. You might see some microductility when you put them under the microscope. Interesting here is, as I mentioned, is that there was a complete knockoff on the design, including the hexagonal nut feature that you see here. This feature invites the use of a tool. But if you look underneath the coupling nut, very poorly, I might add, put on the coupling nut, you can see it says hand tighten only. But again, this is inviting a tool. Now, if you look at the label that's on here, even though this says hand tighten only, look at what the label states. It says, do not conceal behind walls. Okay, understand. But this label says hand tighten plus 1/4 turn only. Well, that means you have to use a tool. So this is a very confusing warning. When we're going to go from going from a metal to a plastic, it's important that the end user understands that there's different rules that may apply here. Here, using a tool. And you may need to put warnings on. It's very important that you use the right warnings. And you should be using the ANSI Z535.4 and 535.6 to create your warnings. They need to be obvious, which means you have a bold color, you have a diagram that shows, hey, don't use tools, it's very obvious. If in the writing it says what not to do, it says what to do, and if you do it wrong, what is the consequence going to be? Now let's look at this coupling nut a little bit more in detail. Here you can see the thread. This is a cross section, and here you can see the flange or the rubber seal that the male makes contact. So the male gets threaded on, and it makes contact right about here, and that's very important. And it creates a seal right here. So it threads on and threads into about these first 2 or 3 threads. Okay, you should see here now when it makes contact, it's going to press down on this thing, on this rubber gasket here, and it's going to put a huge amount of stress right in this area. Okay, right where you see this very sharp corner or transition. The thread we shouldn't be using is being used on this part. Look at how, and that's right where the cracks take place. If we round this off, we can gain about 3 times the strength of this part by just rounding that off. Better yet, why is the thread all the way down to the end? The part isn't threading all the way down here. Eliminate this thread. Thread it only to this area as far as it needs to go. What's going to stop it is this right here. The thread it's not going to go down here, and now you're going to have a thicker wall this whole distance, and more importantly, you're not going to have a sharp transition where that high stress is. Understand where the high stress conditions are and get the sharp corners out of there. Let's a little bit more in detail why this failure took place. Some people might have seen this graph that I've shown below. This is a very important graph. It's basically showing you the strength of the material over time. These are the points where the material will fail in time at different stresses, like I sort of showed earlier. course, the lower the stress, the longer it takes for the part to fail. Now, these coupling nuts are typically made out of polyacetal. And if we design this nut and we know that we do some FEA and we say, okay, the part's going to see 35 megapascals of stress. No, this thing's going to have about 70 megapascals of strength. No problem. We have a factor of safety of 2. No, it's not going to fail. But as we march in time, we have this constant stress there. The load is still there, but the molecules are moving, and effectively the strength of the material is going down. We're going to hit this graph, and when we do, we are going to have failure, and we're going to have a creep rupture, brittle failure, as it's seen here.
Thank you for watching. If you enjoyed this video, please hit the like button to let us know, and comment below with any questions or topics that you would like to see covered on the channel. Also, remember to subscribe so you do not miss any of our new content. If you have a specific problem you would like one of our experts to discuss with you, please reach out at the contact information in the description below. See you in the next video.